All right, so once again, I want to welcome you to our third lecture, and today we are going to be looking at the basic network concepts. Before we start, I want to maybe try and find out from you, you as a security engineer, why do you think even you need to, be concerned with looking at some of the few network concepts? Just you can just tell me what you think, and so that throw your thoughts out. And I get to hear from you.
Morning, everyone. So basically, networks covers basically the transport infrastructure over which services are built, resources are shared, and interaction basically happens in the system design.
All right. Thank you. Thank you for sharing. Anyone else?
Hello, class. Joseph here. Basic network concepts. We need to understand these so that we know how to protect them from attacks. That is why we need to understand what we're protecting, how it works, and how to protect it.
All right. Thank you. Thank you for sharing. Good enough. We have quite a number of network engineers on this forum. So on, I think on too many occasions, we will we'll be hearing their thoughts and what they think about this concept. So, Winfred is saying that we also need to look at networks because we have threats to information through the network. And Daniel Okot is saying that networking is a basis of flow of data and protocols that can help the security engineers plan accordingly. All right, so thank you all for sharing. I think it's time for us to get into today's class.
Before you continue, Ahmad has something to say. I see him raising his hand.
Oh, okay. Yes. Oh, yes, Ahmed. Thank you, Winfred, for that reminder.
To come up with a proper security model, you need to have a clear insight of different network concepts. So that is probably one of the reasons why we look at different network technologies and concepts.
All right. Thank you. Thank you for that. Let me just configure my pen here, and then we are able to start for today's class. All right. I think we're good to go. Okay. So today's we're going to be looking at the basic network concepts. And to understand security technologies, you need to first learn about the basic network concepts, such as basic communications. If you send out a message from your WhatsApp device to your colleague on maybe in the US or even in Uganda on the same WhatsApp device, how are these devices going to be able to communicate? How is your Zoom even being able to communicate and we are all connected and we're in this conference call? What are the underlying communication principles? What components are going to make up our network? And of course, the common network protocols. So with knowledge of these basic concepts, you can better understand network security threats, and deploy security defense mechanism or policies accordingly. So moving forward, upon completion of this course, you'll be able to describe the principles of TCP stroke IP protocols. This is a protocol suite. We are going to be looking at it, talking about it, because this is not a networking course, but we shall just talk about it. And then, of course, describe the working principles of common protocols, and then describe possible security threats to common protocols. So let us look at the TCP stroke IP architecture, the common architecture, maybe at the campus level, university level, or even at an enterprise level. So at an enterprise level, you find that usually network engineers design their network in a layered kind of manner to, be able to control the network. And I must emphasize and mention again that this is not in one room. This is the logical layout of a network. So don't look at it and think that this is going to be in one room. So according to this diagram, we have different layers. We have the egress zone, we have the core, we have the aggregation layer, and of course the access layer. Now, in the traditional network, usually it contains the core, the aggregation, and the access layer. The core layer provides high-speed data channels. This layer, that's why you are seeing it's having, usually this is where we have the layer 3 switches and of course more powerful devices to help us provide high-speed data channels. And the aggregation layer converges the traffic and control policies, and the access layer offers various access modes to the devices. This is our aggregation layer. You must know that in about, I think, medium or large networks, like let's say a network covering your campus network, someone designs the network in a way that it's going to work in a split network function. So within each module, consideration must be given to the flexibility and scalability of the network structure. So generally, the hierarchical architecture is used, and like you see in this example, the network needs to provide access services to a large number of users. So at our access level, this could be a switch maybe at block A. Let me try and move this a bit up. This could be a switch maybe at block A. This could also be a switch at maybe, let's say, another block, or even at the up campus, up country campuses. And this could be also somewhere. And on these switches, maybe on ground floor, on, first floor, third floor, and they could be maybe put in a, in a rack, in a network rack. And on those switches, you have a number of end users connected to our access layer. And maybe you could even have your access points around here, which are also connected to that port, and they are giving Wi-Fi or Wi-Fi access to your end users. And you could also have other access points connected to this. So this is all done at the access layer. So our traffic is all now converged to our aggregation layer, but as you can see, it is converged to our aggregation layer in a manner that is in a redundancy mode. Why it is done like that is to ensure that there is a redundancy and there is reliability of our networks. You see this switch here from our rack here, it is connected both to our device here and also to our device there. So in case this device would be off, our person or our end users communicating from this device would still be able to send out packets and be able to communicate either to our wide area network or even out to the internet. So today, most companies are connecting to their wide area network through the internet. So, and of course, it entirely depends on the architecture and how the system was designed. So let us look at some of the modules. So for us to be able to have, our network, and we have the different devices, we have the switches, we have our firewalls, we have our routers, and so many other devices that may be part of the network. But then how the hell are these devices going to be able to communicate? How are these devices even going to know that I am not supposed to do this, or I'm supposed to send this, or when I'm sending this, I should consider this, or I need to make sure that there's no loop, or I need to make sure that I use this protocol. And if I'm following this protocol, I need to use this port number. And if I'm using this port number, this is what I'm supposed to do. How do they even get to that level, and how do they even get to know that this is exactly what we need to do. Are you guys hearing me?
Loud and clear.
Loud and clear.
Yes.
Oh, okay. Okay. I think today people have just been disciplined in terms of muting their microphones, because I was wondering, I was not getting any interruption. So we are going to look at the OSI model. The OSI model, and we're going to learn more about the OSI model. But basically, the OSI model is an open system interconnect reference model. Basically, they came up with these models to help us, have a standardized. Yesterday, we looked at standards. So to help us encourage the development of standardized protocols to enable and to make sure that if I send my data or my email from my phone, I'm sure who is going to receive it on any device, they'll be able to receive it successfully. Imagine if maybe Apple Talk was using its own, protocols, and you're also using IP and IPX, and some other guys are using their own protocols, and we don't know. Also, some African decides to, come up with their own protocols, and how, and some Chinese guys also decide to come up with their own protocols. At the end of the day, we wouldn't have standardization. At the end of the day, we would not be able to communicate effectively. You'll find that some devices are incompatible, and that's the beauty of standards. Because of standards, you are sure that even if you got a USB from Africa and you went with it in Asia and you found a computer, any kind of computer, you'd still be able to access your information, isn't it?
Yes.
All right, so we are going to look at the objectives and why these people decided to come up with the OSI model, and try to understand the designing principles and, of course, the advantages of the OSI model. So, but the OSI model basically is the OSI model basically, it is a reference model. Like I told you, the OSI model, it was designed to overcome the interconnection difficulties and the low efficiency issues associated with using many protocols by defining an open and interconnected kind of network, right? So this reference model forms the basis for computer network communications, and its design complies with the following principles. They have quite a number of principles, but one of the principles is boundaries. They decided that even when we are coming up with our layers, there should be clear boundaries between these layers. What they do should be clearly clearly identified, and we should be able to know what is done at each layer. Each layer is implemented or implements specific functions and does not affect any other layer. So each layer works, and even in the process of it functioning, it does not affect any other layer in any way. And each layer is a service provider and a service user. They both serve each other. Layer 1 will serve layer 2, and at some incidences, layer 2 will also serve layer 1. Those are some of the principles that we were talking about. So, of course, there's also the divisions of layer, which also encourages development of standardized protocols and sufficient layers to ensure that the functions of each layer does not overlap, that we don't have a duplicate of functions in the different layers. So it has the following advantages: that because it simplifies network operations. It simplifies network operations because even when you're troubleshooting on your network and you are somehow trying to reach a computer, you're sending a ping 192.168.2.8 and you're not getting any reply, you know that you need to troubleshoot starting from layer 3 and below. There could be the problem from there, and then you start to see if maybe and see how best you can troubleshoot. If for some reason you are not being able to do something, let's say that there's not data transmission, maybe you have to cross-check and check out on your data link layer. So it also provides standard interfaces that support plug and play compatibility. Here, because you have standard already, you have standard protocols, it is easy for vendors to come up and make devices. You know that you can use different devices of different vendors on the same network, and you'll still be able to, you know, somehow come up with a good functioning, robust network. And of course, it also enables other vendors to come up with devices. Of course, it also prevents a change in one area of a network from affecting other areas. So if your area, let's say your session layer has issues, you'll still be you know, protected, and it will not affect the other functionality of other layers. So let me ask we have people here. We have been talking about layers. How many layers are in the OSI model?
There are 7.
They are 7. Perfect.
7. Yes.
Thank you. Thank you. Someone in the chat is saying that my audio is on and off. Is that true? Or it's their network?
Oh, yeah.
It's
Their network, I guess.
All right. But you're getting me loud and clear. Okay. All right. So moving to the next slide. Moving to the next slide. We want to look at these 7 layers which you have told me about. And as you can see, there are 7 layers. The 7th layer is our application layer. We have our session layer, our presentation layer and our session layer, our transport layer, our network layer and data link layer, and our physical layer. So in the OSI model, units of data are collectively called protocol data units. They are called PDUs. But however, like we said, each PDU is called a different name according to the layer at which it is going to, at which it is sent, right? So we have our application layer, and our application layer, this is where communication happens between different applications. You are using Zoom, you're using your browser to send, you know, packets, or you're using your email client like Outlook, you know, to send out your emails. So this is a layer that is responsible for taking care of for taking care of such kind of communication. And later on, we shall also look at some of the protocols that we use as part of this layer, right? But like HTTP and other HTTPS and other protocols are some of the application layer protocols that we use on our 7th layer, and its its protocol data unit is called the application protocol data unit. And also we go to our presentation layer. So our presentation layer helps us to process data formats, and it encrypts data, right? It helps us to, you know, to process our data formats. What data am I receiving from my application layer? Is it a video? Is it an image? Is it an audio file? So it's going to process all these formats, and then it's also going to help us with the encryption and a decryption of that data in case it is the one which is receiving to send up to our 7th layer. So this is our presentation layer, and like we said, it's a protocol data unit is called the presentation protocol data unit. And then also we look at our, you know, session layer. And our session layer here, what it basically does, it helps us to establish, maintain, and manage the different sessions. You know, it's going to establish the session when you are, you know, you're in the process of communicating, and also to maintain the session. Of course, it's going to also manage the sessions. And its protocol data unit is called the session protocol data unit. So after establishing the session, it will go ahead and it will forward the packet. We shall look at how data is encapsulated later on, but it will go ahead and send the packet all the way to the transport layer. So when it gets to the transport layer, this helps us to establish our end-to-end connections for our hosts, right? And after that, we are going to look at our data. It's will also sometimes be called the transport protocol data unit, or its other name is what we are calling the segment. The first three layers which I've talked about lie in the top three layers, and the other and these other ones lie in the bottom four layers. So we have looked at the transport layer, and we said it helps us to establish end-to-end connection sessions for our hosts, and its data packet is usually called a segment. And here we're going to forward our packet, and our packet is going to be forwarded here to our network which is going to forward our packet. So our network layer, it performs the addressing and routing. This is where you talk about IP addressing and talk about routing and so on and so forth. So this is done at this layer, and this is where we look at a packet, right? So our packet is sent, and now we look at our data link layer, which is the second layer, and it provides media access and link management. And the data link layer deals or handles frames, and it's going to forward our frame and then to the physical layer, which transmits in bits and streams of ones and zeros. Basically, here we are looking at we are looking at the medium being transmitted, the data that is being transmitted and converted into the electronic mode. So each layer of the OSI model encapsulates data to ensure that the data can reach the destination accurately and can be accepted and executed by the terminal host. So if a node encapsulates the data to be transmitted by using specific protocol header for transmission, when that data is processed by the layer, packets are also added to the tail of the data, which is also called encapsulation, and we shall be looking at it in the next slide. So like we said, each layer uses service provided by the lower layer to communicate with each other, right? So if host A wants to communicate with host B, it will go ahead and send a packet which will pass through all the, layers. At the same time also, they will also have to go and pass through the different layers. So a physical layer involves the transmission of bit streams over a transmission medium, and it is fundamental in the OSI model. This one is what implements the mechanical and electronic features. This is where we have, maybe I'll just go back a little bit and ask some of you to tell me some of the the devices we have at the physical layer. Which devices do you think we have at the physical layer? Our networking
Switches,
physical layer.
switches, hubs.
Okay, hub is here. Cables, yes. Repeaters, yes. And how about the data link layer? Someone in the chat has said switch, but we need to be also very specific. Layer 2, switches, network interface cards. All right, how about the internet layer?
Routers, access points.
Access points.
IP addresses.
All right, the protocol of IP address.
No, access point and data link layer.
Access points. All right. If it's a layer 2 access point, then in the data link layer, if it has routing capabilities, then it is a network layer, and of course layer 3 switches. All right, so let us move to this end. So we are saying that this we are looking at the physical layer, and we are saying that our physical layer looks at the electronic and data transmission, and this focuses on only how to transmit bit streams to the peer end through different physical links. Yeah, and the information contained in each bit stream, for example, addresses or application data, is irrelevant at this layer. For them, what they focus on is the bit streams to forward them through the cables so that they go all the way and reach the intended destination. So some of the typical devices we have talked about already are the repeaters and the hubs. All right. Just a moment. Excuse me, briefly. Just to highlight, please, if you are part of this class and you know I'm in class, do not overcall me. Kindly, I'm just requesting. You can call me after the class, so that I concentrate and give my students the best I can. All right. So we are saying that the main task at the data link layer, the main tasks of the data link layer. We're talking about the physical layer. Now we are going to
Application
talk about,
layer.
we're talking about the application layer. No, I've been talking about the physical layer.
Oh, okay.
Yes, the physical layer. And for it, I'm saying it is concerned with transmitting your bit streams to the peer end, right? And some of the devices here at the physical layer, we said we have our hubs and we have our repeaters, right? And of course the cables, just like you told me. So the main task of the data link layer are to control the physical layer and also to allow to control the physical layer and also to allow it to present an error-free link to the network layer. All right. So it also helps us here. It helps us to check and also present an error-free link to our network layer to detect and correct any errors and also to perform traffic control. This is done at the data link layer. Which layer is this?
Layer 2.
Layer 2.
Layer
This
1.
is layer 1. Right.
The data link layer.
All right. So now we look at also the network layer, and we say the network layer is for forwarding packets and checks the network topology to determine the optimal route for transmission, right? It helps us to, it's responsible for forwarding the packets, and it also helps us to check the network topology to determine the optimal route. We shall look at that later on, but it is crucial to select a route from the source to the destination for the packets. So the network layer device calculates the optimal route to the destination by running a routing protocol such as the RIP or using some functionalities like the trace route. It identifies the next network device, which sometimes the network engineers call the hop, to which the data packet should be forwarded, and of course encapsulates the data packet by using the network layer protocol and sends the data to the next hop by using the service provided by the lower layer. Imagine you have your network like the first diagram I showed you here, and you have quite a number of devices, and your end device is here. And for it to be able to send the packets, remember, you need to know the source. You need to know the source MAC address. Of course, you know it because it's your computer. But then also you need to know the destination MAC address, and you also need to know the source IP address and the destination IP address. But then how is it going to be able to know when we have quite a number of devices? Which route is it even going to take anyway for us to be able to reach our computer or our device which you want to communicate and talk to here. One end user is here, another end user is here. How is it going to know that I'm going to follow this route and then go like that and then come and then I'll be able to talk to my end user? I don't know if you are getting the picture, but we are saying that it is this, at this layer, which is layer 3, which is responsible for helping us to calculate the optimal route and also for forwarding our data packets, right? So that takes us to the transport layer. And we said in our transport layer, the transport layer is responsible for providing effective and reliable services. Generally refers to the application at the application layer for end users to use. All right, so okay, so moving to the next slide. First clear my screen a bit. All right, so we are now going to map the TCP and the OSI model. I didn't mention earlier on, at first it was the OSI model, but later on they came up with another protocol suite which we are calling the TCP/IP. And that TCP, or which they call the Transfer Control Protocol / Internet Protocol, it is a model which is widely used due to its openness and usability. The TCP/IP protocol stack is implemented as a standard protocol, or as a standard protocol. So this model is divided into 4, like the way you can see here, where we have from the bottom, we have our network access. We have our network access layer, or which sometimes people call the link layer. And we have our internet layer, and then we have our transport layer, and then we have our application layer up there. So some documents also define the model with 5 layers, where they go ahead and the link layer is split into 2, having the equivalence of the data link layer and the physical layer. Yes. So this is the mapping between the 2. So what they did, they decided to get the application layer, the presentation layer, and session layer, and combine it into one layer at the top. You remember that our top 3 most layers, they combined them into one layer in the TCP/IP model, which is called the application layer. All right. So moving forward to the next slide. So in the TCP/IP, each layer of the TCP protocol stack has corresponding protocols, right? And which are achieved to generate network applications. So some protocols cannot be defined in a hierarchical manner. For example, like we're using the ARP, we shall look at it later on, and of the ICMP. These ones are developed at the same layer as the IP protocol at the network layer. However, in some scenarios, you can use the IMCP and it can be placed maybe at the upper layer of the protocol. And also the ARP, the address resolution protocol, can also be placed at the lower layer of the IP protocol. So that's why here it is robust and it's also a bit effective. So let us look at the application layer, which happens to be which layer here? Layer what?
4.
Layer 4. So let's look
Layer
at the
7.
application layer,
Oh,
which
4.
happens to be layer 4 in our TCP/IP protocol suite. So we have these different protocols: HTTP, Telnet, FTP, TFTP, and DNS. Who can tell me what do we use HTTP for?
They are used for websites
Browsing.
at the beginning of the
HTTP is transmitting text.
Browsing.
Okay, how about Telnet?
Remote login.
Remote login. Okay, how about FTP? FTP?
Download.
Download of what?
Large files size.
How about small small files?
TFTP.
Okay. How about this?
Address translation.
Address translation.
Translation.
So the application layer in our TCP/IP protocol, this provides network interfaces for applications, all right? And when we look at our transport layer, which happens to be layer what? Layer 3, it has these protocols. We have our TCP, which is a secure connection, and we have our UDP, which is unsecure connection. Could someone tell me why I'm saying UDP is not secure? Well, I lost you from there. All right.
Having to control flags.
Okay. With UDP, it is a connectionless protocol. For you to be able to communicate with another device, it does not first require to establish a secure connection. As long as you want to send to that destination, it will just go ahead and send the packets. And it is used more so for, files which use like video streaming, video sharing, because I mean, if you're watching your TV, you do not want to, first send the, the handshakes and, establish the connection to receive one packet, then another packet. At the end of the day, you may not get, a clear, stable picture for you to view. Whereas TCP, we shall look at it later on. For this is it has to first establish a connection between the sender and the receiver, and we shall be looking at it. So on the transport layer, it's just like that transport layer in our OSI model. It establishes an end-to-end connections for the host. Whereas the internet layer here, which happens to be our layer 2 in our TCP/IP protocol suite, it has the IP, IP protocol, the ICMP. What is ICMP used for? All right, we have the IGMP, we have the ARP and the RARP. And here, it helps us to perform addressing and routing, just like that's what it does
Excuse me,
in
sir.
our network layer in the OSI
Excuse
model.
me,
Yes,
sir.
please.
Some of the now, okay, let me say again. ICMP in full.
Come again.
Like some of these words, ICMP, IGMP, I've forgotten their
ICMP is Internet Control Message Protocol.
Okay.
All right, but like I said, this is don't beat yourself too much. This is not a networking course. This is a security course. But if you want to find out more about networks, there's a HCIA routing and switching. This is a purely a networking course offered by Huawei, so you can go ahead and take up the course. But worry not, we shall also take off some time and look at some of these protocols, more so the protocols that are relevant to us as security engineers. And then lastly, our layer 1, oh, what have I done? Our layer 1 network access layer in our TCP/IP protocol, and we have our Ethernet, different standards of Ethernet, 802.3, our PPP, HDLC, and FR. So these are some of the protocols, and there are quite other more protocols within this suite, but they're just mentioning a few of them. And this performs the physical media access, just like the our data link layer in our OSI model. So moving forward, we want to look at the encapsulation and decapsulation process of the TCP/IP. We have our sender here and we have our recipient. So our sender, the sender submits the user data to the application layer, and which then sends the data to the destination. The encapsulation process goes through all these processes which we are going to talk about now. So the user is first, the user data is first transmitted to the application layer, and the application layer a trail is added, right? So when the sender sends the information, this is when we are encapsulating. Our application layer is going to get our packet, and it is going to add there our application trail here, packet on our user data, right? Let me use something else to draw. Okay, let me just clear that. Okay. All right, so I was saying that as our data is being encapsulated, here our application layer is going to get this and add our packet onto it, right? So after the application layer has processed, or the processing is complete, the data is transmitted to the transport layer. The transport layer here also will go ahead and add its packet onto our data, which we have received. It will add its packet onto that packet. And those packets include different things, right? The application protocol here now specifies whether it's going to use what protocol. Are we going to use the TCP protocol, or are we going to use the UDP protocol, right? So that protocol, or that kind of protocol, is added onto that packet, which is going to be sent onto that unit unit data protocol, which is going to be sent. So then after that, the transport layer will forward our data to the internet layer, and after processing, after the internet layer has done and received the data, then the internet layer information such as the source IP address, destination IP address is then added onto our user data, right? Then the data is added onto our user data. So after the data is processed by internet layer, the data is transmitted to the network access layer, and the network access layer adds the protocols such as Ethernet, the ones we talked about, Ethernet 2 or either 802.3 or other protocols, and then the data is then finally transmitted to the destination as a stream bit. Processing differs based on the different devices, right? So if that example is sent, it will come all the way up to this side. So after the user data arrives at the destination, the decapsulation process is then also performed, right? Let us look at we're going to look at the decapsulation process, but just hold on, just excuse me just a little bit.
We are not getting.
I can't hear you.
I think it is intentional because the instructor is not on.
Yeah, I had asked you to excuse me a little bit. My sincere apologies. I've put now my phone in do not disturb mode. Some people are calling me, they can't join the meeting, they're not seeing the link, and you ask them if they're in the WhatsApp group, they are there. I don't know how they cannot see it, the link for the class. Did I forget to share it? Maybe if you could remind me.
The link is
The link is there. The link is there. I
The
think
link was
it is in
shared.
there
After it
in
is
the WhatsApp
noticed.
also.
All right. So like we had said here, after now, our data is being sent. Now, how is it going to be decapsulated all the way up to when it reaches the intended recipient? So it will also go to, it will go to our network access layer here, and our access layer will now look at these different, protocols which they have used, and it will process it accordingly. And of course, look through the IP address, and so it doesn't look through the IP address, and it will strip off the Ethernet, packet, and it will forward the data to the internet layer. Internet layer will also look at the different data or the protocols which were used, either if it is IPX or IP, and it will go ahead and process the user data and forward it to the transport layer, which will do its role. And also after checking and cross-checking through the packets, it will strip off the that, and it will go ahead and send our data to our application layer. The application layer, remember, it has all the sessions. The presentation layer will look at the data format. It will look at the session maintenance and all that. And after, it will strip off, and then our user data will be decapsulated, and our recipient will be in position to receive our user data. So Quanti, just looking at Quantipo.
I have a question.
Yes, please.
Encapsulation, is it encapsulation and decapsulation can we say is basically decryption and encryption? In other words?
Not necessarily encryption, but something like that, but not necessarily encryption. Do we have network engineers on this forum?
Can you say encoding then decoding?
Encryption. Can I what?
Can you say if it's not encryption, can we say is it encoding and then decapsulation being decoding?
Yes, something like that.
I think his analogy is true, because every stage that the information is passed on, there's an additional layer of information that is added as it moves through the OSI model or the TCP. So once it arrives at the destination, it also now starts removing those extra layers to get to the final information that was intended for the destination. So I think he's also correct in his explanation.
True. But also maybe just to add onto that, with encryption, it's not about hiding, right? It's not about hiding, but rather, with encapsulation, it's not about hiding, but rather adding the necessary information or packet trails to the user data for the concerned layers to do the needful, right? Whereas encryption, as you know, it is intended to basically convert the electronic data into a form which cannot be easily understood by anyone else, right? Except the persons or the people who have the keys, isn't it? So that being said, with encapsulation, this basically you're just wrapping your data into some kind of packaging. This is the packaging. You have put the manual, you have put the things they'll use to unbox the phone, you have put the SIM pin card remover, you have put maybe the warranty card and everything. That is more like you're putting everything and wrapping it up together for sending, right? So that whoever receives it has all the necessary information that needs to be, like you have encapsulated everything into that packet normally, right? Whereas encapsulation, you're basically changing the data itself. you're going to convert it into some kind of algorithm, right? Some kind of algorithm that is going to be unreadable to someone unless when they have access to decrypt that kind of data. I don't know if I make sense.
Yes, I basically encapsulation and decapsulation is now constructing a message so that it might take a given route to reach the destination that it's intended. I got it.
But also encapsulation is a protocol. Yeah, these are protocols, whereas encryption is okay. These are protocols.
Okay.
For sending data packets over.
All right, I got it. Thank you so much.
All right, so let us also look at this word here. Who can pronounce for us the word? This word here?
Quintuple.
Quintuple. All right, so let us look at the quintuple structure. So basically, when you're looking at the quintuple structure, we are interesting ourselves with the source IP address, with a destination IP address, the protocol we are going to use. For example, if you're going to use TCP, and if you're also going to use UDP, right? If you're going to use UDP, and then also the source port and the destination port. Now, these 5 things are what make up these things that we're seeing here are what makes up our quintuple, right? So the destination port, generally well-known application services have standard ports, right? Such as HTTP. Who knows the port for HTTP? Oh, of course, it's already here. but yeah, they have standardized ports, though you can also go ahead and change them depending on the need, or maybe for security purposes or reasons, you can go ahead, or FTP or even Telnet, right? These already have, their default ports. Who can tell me the ports for FTP?
Port 20 and 21.
Port 20 and port 21. And the source port usually basically is common application services such as HTTP still and FTP still. They also get the source port. So the quintuple is a concept so that an application server can respond to service requests. It must register the port numbers and the protocol for the services it hosts. By using the quintuple, the application server can respond to any concurrent service request while ensuring that each link is unique in the system. You have ever wondered, when you're sending out packets, you have your web browser, you have opened your web browser and you have quite a number of tabs, right? Quite a number of tabs. You're accessing this server, you're accessing Facebook server, you're accessing Google, you're watching YouTube, and they're all sending out packets. And these packets are all going out with the, HTTPS, yeah, right? They're going out with HTTPS, probably, the default, source port. And how is your system going to be able to know that this packet we sent there, when it comes back, we are going to put it on the Facebook tab, and when it comes, the other packet that is going to be received is meant to go to, your email or to Facebook? Yes, please. Yes, please.
I may go to the question. When we talk of a port, exactly what do we mean?
When you talk of a port, exactly, what do you mean? Members, what do you think?
Eating my mind.
I can try.
A port is like hello.
Yeah, I think a port is a direction, a route at which a gateway at which packets can be sent and received. That's what from my understand. Like, yeah, it's like a path or like a door somebody can use to go in. Let's say if you want to go to the kitchen, you use the kitchen door. If you want to go to the toilet, you use the toilet door. So that's what I understand.
Okay. Thank you for trying. Anyone else?
I think it's a specific number.
I have weird users who normally. Hello.
Hello.
Yes, please go ahead.
I think a port's like it's a unique number like identification of a network, maybe from the host to the final receive of the message.
All right.
Like
You're
the host
all
has-
correct. Yes. Okay, you can try.
I think a port is a virtual point where network connections might start or end.
Okay. All right. Thank you. I think they have explained it well. You asked a port, but you not specify. Just like think of it like you see a physical port on your computer, right? You have ports on your computer or even ports in your TV, right? And you say, hey, I need to put my flash in, my USB port on my TV or on my console or in my computer or anywhere, depending on the kind of port you want. So just like our colleagues have said, it is basically more like a location or like a point of connection where information can be sent, right? Someone was saying, excuse me. All right, so shall we continue?
Yes.
Okay, so we also look at the common network protocols. We are going to be looking at the common network protocols. We have here some of the protocols listed here. As you can see in the diagram, we have our OSPF or RP. These are routing what? Routing protocols. We have our ARP. What is ARP in full, team?
Address resolution protocol.
Address
resolution protocol.
What does it do?
To get a MAC address of a certain IP address.
All right. How about the SNMP? What is it in full?
Simple Network Management Protocol.
What does it do? All right, so we shall continue. So we are looking here at the address resolution protocol, and we say that when a packet is forwarded from one computer to another host or gateway in our network segment, but in the same network segment, the destination address is known and the MAC address than the corresponding address. So to the destination address, it has to be obtained. So in the same network segment, the MAC address is used for communication. So when you have your computers and they are, let's say 192.168.0.100 and you have 192.168.0.8. Are these two IP addresses in the same network segment?
Yes. Yes. Yes.
Yes.
Okay. Which class is this?
Let's see.
Okay. How about these IP addresses? .13, 192.168, 168.2.13. Are they in the same network address?
No.
No, they're indifferent.
They are indifferent. Okay. How about 192.168.1.13.12/24 and 172.1.13/24. How about that?
They are indifferent.
They're in different networks?
Yes.
Okay, interesting. So anyway, for the people who are wondering where these people are getting all those things from, worry not, this is not a networking course, and do not, be there and you feel like you are being left out. But we are looking at the ARP, and we're going to also look at it in detail. But basically, what happens, we said for computers to be able to communicate with each other, we need to know two things, right? We need to know if they're the same network, we need to know the source MAC address, isn't it? And the destination MAC address for this guy to be able to know that. So if he doesn't know what it will do, it will send an ARP to the computer and asks the guy, guys, help me out. Who is the owner of this IP address of 192.168. let's say 2.20? Who is the owner? And it will send out and wait for the response. It will flood the entire network, and all other computers will get the same broadcast message, because the MAC address, we don't know the destination MAC address, so they will all be zeros, right? The MAC addresses will be zeros, or it will be a broadcast MAC address. So it will be sent to all the computers, and all computers will receive it. So when the computer receives it, we'll check and see if actually this is its IP address. And if it's not the IP address, it will disregard the packet. If it is the IP address, then it will send an ARP response or reply to the computer and tells the guy, hey, I heard you're looking for me. What can I do for you? But in the meantime, it will also update its MAC address table or its MAC table with the entry of the, the guy, because already it has the source IP in the packet which was sent to it, and it will update its details, and also it will go ahead and send this guy a response, and this guy will be able to know, oh, it will send a unicast packet. It will not broadcast to all other guys in the network. It will just send a unicast packet, and this guy will be able to know that, oh, so whenever I want to communicate to this guy, this is my destination MAC address for this particular IP address. So this guy will also go ahead and also update his MAC address table or his MAC table. So that is the ARP. We will also look at it, and also let us look at IMCP. So the IMCP is used to test network connectivity, and the typical applications that most people use are, could someone help me guess?
Ping.
It is ping, very good. And
Trace route.
And trace?
Route.
Trace route.
And trace route. Perfect. When we use ping, if we want to find out if our host is reachable, isn't it?
Yes.
And we
Yes.
use trace route when we want to do what?
To see the route that the packet is taking.
Okay, to see the route.
When you want to get the destination IP.
Checking the hops.
Okay. So basically that is it. And our routing protocol is here. We have OSPF and RIP. We are going to look at them later on, but basically they are used also to test our network connectivity. They're used for communications between users in different network segments, right? And also they help out in eliminating and making sure that there are no loops in our systems, and we shall look at them, worry not. And just like our colleagues told us, the SNMP is a network device management protocol that is going to help us to manage our simple. Let me check the chat. I'm seeing the messages popping. I am, please add me there. Okay. Someone who is asking me to add them to the WhatsApp group, kindly, just if you're on Telegram, read through the messages that were sent. The link was shared. I have so many requests to work on, and I may not respond to you promptly, but I will go ahead and I don't know if Winfred here is also in the WhatsApp group. I will try and make more other people admins and also in the Telegram channel so that they can help out on some of those issues. All right. The Telegram link, it was also shared. Let me see if I can post it in the chat now so that we get done with that conversation. Okay, let me look at. Allow me to do that after the class, because I realized it was going to take my time. So we're saying
I've shared all.
You have shared all. Thank you, Winfred. I'll also go and make you admin so that you can help out some of those people. But thank you once again. So I was saying that we're also going to look at our net stream here. We shall talk about it briefly, and it's an information sampling protocol. It is usually associated with other devices such as the anti-distributed denial of service devices, right? So let me clear my screen and move to the next slide. So we talked about the ARP and we already talked about what it does. So before sending a data packet, like we agreed before, host C and host A needs to obtain the MAC addresses for host C. Sorry, before sending the data packet to host C, our host A here, it needs to obtain the MAC address of host A. If this guy wants to send packages to this guy, he needs to first know the MAC address of this particular guy. So if he doesn't know the MAC address of this guy, he will definitely send out an ARP to make sure that he gets to know the MAC address of the guy. So by using the ARP protocol, a network device can establish a mapping between an IP address and a MAC address. After obtaining the destination IP address, the network layer or the network device needs to determine the destination address, the MAC address, and it's just to make sure that the destination MAC address is known, right? So that is what happens. So it needs to know this guy. If it doesn't know what it's going to do, like we said before, this guy is going to come up with a request and say, you know what, host C, I want to send you something, but I can't communicate with you because I don't know. Actually, probably he may not even know that it is host C, but all it knows, it has its what? It has its IP address, which it wants to communicate to. The IP address is known, but it doesn't know the MAC address. But we said for them to be able to communicate, we also need to know the source and destination MAC address of the intended or the device is intending to communicate. So what it's going to do, it's going to come up with our ARP packet. And with our ARP packet, it has our Ethernet 2 frame. And our Ethernet 2 frame, which is must or which has to contain both our destination MAC address and our source MAC address. But if you realize in this illustration here, we have our broadcast MAC address. Why? Because we do not know the MAC address of our destination. So we put there a broadcast. And our source MAC address, we know it because it's our computer. This is our source MAC address. So we are happy and we know our MAC address, but we don't know the destination MAC address. We know our IP address, the guy which we want to send to, but we don't know where he's seated. We don't know where, we don't know which host number. And we have our source IP address. And now we are going to go ahead and you see our destination MAC address now in our ARP is full of zeros because this is a broadcast MAC address because we don't know it, and we have our source MAC address. So we are going to put in our ARP request and send it out. What is going to happen, like you see in these arrows, I'm going to send the request and it's going to go to all the computers. And it's just a request saying, guys, please, I am looking for this person with an IP address of 10.0.0.3, but I don't know where I can find him. Can someone help me try to understand where I can get this guy? So this guy will see this request and he will look at it. Sorry, let me try and grab these things. This guy will see this request and he will look at it. And after looking at it, he will say, but you know what? This is not my IP address. I understand this guy wants me to, but this is not my IP address. Therefore, it's going to go ahead and it's going to discard the packet. It's going to go ahead and discard the packet, and it's going to drop it, right? It's going to drop it. And then when this guy, host C, receives the packet, he's going to go ahead and look at his IP address and says, oh, wait a minute. So this guy all along wanted to talk to me. Oh, I am the guy, I'm the guy, I'm the guy. So she should definitely reach out to me. I am the one. My pen is disturbing me. I am the one, so he should definitely reach out to me. And he will go ahead and he will update his mark table, and he will go and send a unicast. He will send back. Let's look at the response. He will go ahead and send back the ARP reply. With the ARP reply, he will go ahead and update his ARP table, and after updating his table, he will update it with also the guy who has sent his details on host C. He will update it like, oh, there's also this guy on the network. Let me also store his details in case I need to talk to him, because I'll need his IP address and I also need his MAC address. So let me go ahead and store his things in my MAC table and keep them there. You never know, I could be in position to also later on want to establish a communication and send him details. So he will go ahead and send a unicast frame or unicast packet to him, and this guy will receive the reply with the MAC address of this guy. Remember, in the packet that was sent earlier, this guy already knows, because the source MAC address is here. So this guy already knows that, you know what, the destination MAC address is the source MAC address for the guy who had sent me the packet earlier on. All right, so that is the ARP, request and reply. So he will go ahead when he's sending his packet back, like we said, he's going to get his frame and he's going to put in his destination MAC address for this guy, because now he's sending back the packet, and he's going to go and put in his source MAC address here, and then he's going to go ahead and forward and address the packet to host A, and he will be able to receive the packet. So let us also look at the gratuitous ARP. How do we pronounce this word?
Gratuitous.
To check
Yes,
if
please.
there is a conflict in IP address or what or not.
Oh, okay. You're giving us its use. Thank you, thank you. So this gratuitous ARP can be
gracious.
gracious. Okay, this gracious ARP can be used to detect whether IP addresses conflict, right? So after an IP address is you have been assigned it to the host, the IP address must be checked to ensure that it is unique on the network and does not conflict with any other address. Maybe let me ask, what is the IP address apart from telling me what it is in full? What's the IP address?
It is a unique, it's like a unique identifier.
Keyword unique.
Identifier of a computer
The
on
logical,
a device.
the logical address.
I think it's like a name of a computer, like a specific and a unique one to describe it.
All right, so meaning each computer is supposed to have its unique logical address or identifier on the network, right? So we need to make sure that each computer only and only is assigned one unique IP on our network, or else we'll have conflicts on the network. So that's why the engineers, the network engineers, decided to come up with this gracious ARP to make sure that there are no IP addresses conflicts on our network. So if this hosts sets an IP address in the ARP request packet is to its own IP address, and then it broadcasts the packet. If the host then receives the ARP reply, it knows that the IP address in use and can delete the IP address conflict. So what it does, it goes ahead and puts the source MAC address in our Ethernet frame. It goes ahead, puts it there, and the destination MAC address, since it's going to send out a broadcast, it puts there our broadcast MAC address. And in the destination MAC address, if you pay attention, the destination, this guy here has put his own IP address. Why? Because he's sending the gracious ARP. So he's going to go ahead and he will send this packet onto the network, and it will flood, and other computers on the network will be able to receive it. And in case there's a computer with the same IP address and they receive the same, they will reply. And once they reply, then this guy will know that this IP address is already in use, so it cannot be assigned to me or cannot be assigned to me by either our DHCP server. So if it is just basically used to detect whether there are IP addresses. So introduction to IMC. Some of these things will make a bit more sense when we start, running the labs. But IMCP is used to transmit error, control, and query messages. It's what they use it for. It is one of the core protocols in the TCP protocol stack. The IMCP is used to control packets between IP network devices, to transmit error control, and also to query the different messages, right? So it will definitely send a message out there to the guys, either to the server or to the host or to the intended people, and it will wait for the return message. And it's upon that return message that the network engineer will determine to see if what they wanted to access is reachable, and if you can be able to, to send the response. So IMCP application ping one. So here we have our router, and we want to check and see if we can reach the other router. What will happen? You just run the, the ping, and the ping has different parameters, but the common ping parameter one is the A. What the A does, it usually defines the source IP address. This one, it specifies the source IP address for sending the IMCP echo request packets. If the source IP address is not specified, the IP address of the outbound interface is used by default, right? The other common one is C, the C parameter, which stands for count. This one, okay, Jonathan Olap, I have received your message, and sorry about that. It's okay. You can feel free to excuse yourself. My sincere condolences. All right. So we're saying that where was I? All right, we're looking at the count, right?
Yes.
Yes, we're looking at the count, and this specifies the number of times the echo, request packet are sent. The default value is always 5, right? And we are saying another common one is the H, which is time to live, right? The time to live value, and this specifies the value or the time to live value for our ICMP echo requests. The default value is usually 255. And we also have another one, the minus T. The minus T, it is the timeout, right? It is called the timeout, and this specifies the timeout period of waiting for an echo reply after we have sent our ping. So just in case I wanted to check and see if I can be able to, reach a certain, site, or I can be able to reach my site, let's say, I will go ahead and open my terminal. It could be your command shell, or it could be PowerShell, or anything you're using, or the terminal in Linux. And then you go ahead and you put in ping. And let's say you want to go to which site. I want to go to lms.ssendi to can see if the server is on ssendi.com, and it will be able to send the reply. And after sending the ping, it will get the response, and we'll see that the time to live has been, that, and reduced to that, and then we're able to see the different statistics of that ping response reply. And you can also use your ping with the different parameters, which they have which they have told you, like the minus A, like the minus T, like the minus H, and so on and so forth. And you specify those different parameters in case you want to play with your ping request. But most of those things will be able to make a lot of sense when we start when we start playing with our simulation environments. So this is the ping. As you can see, he has been able to ping an IP address, and it has been in position to return the different results. So the ping command output contains the destination address, the destination address which you are intending to ping, the IMCP packet length and the packet number, the time to leave value, and the time it took the round trip. So the packet is a variable parameter field that is contained in an echo response, and the type, the message is usually equals to 0, and the time to leave and roundup trip time are included in the IP header of the message. Moving forward, IMCP application. We said we were looking at ping. Now we are looking at traceroute, and our colleagues told us that the traceroute helps us to determine the optimal route, or to determine the route which our packets will take on the network, right? And what happens here is a traceroute traces the forwarding path of our packages hop by hop, and it is based on the time to leave value in the packet header. So to trace the path of a specific destination address, the source and end first sets the time to leave value to 1. After the request, the packet reaches the first node, the time to leave times out, and therefore the node sends another time to leave message carrying the timestamp to the stop end. So this means that if you're sending our trace route and this host A wants to identify and find out how they can be able to reach out to host, it will first send a packet with a time to leave. Please take note of that, time to leave of 1. So it will send to this router guy. So when the router guy receives the packet, remember, whenever our trace route is our time to leave value, whenever it's going through our packets, whenever our packets are forwarded, the time to leave value is decremented by, network engineers, by
IP header.
By 1.
By 1, right?
1.
So whenever a packet goes through a router, or wherever the packet is forwarded, the time to leave value is subtracted by 1. So here we are saying when you're using our trace route, what it does, it sets the value of time to leave equals to 1. So when it sets it to this guy, and this guy forwards the packet, it will be decremented by 1, which means it will be 0. So it will leave this, it will come into this interface when it is 1, and it will leave this interface when it is 0. And it is by a thumb of rule, when a router or when a layer 3 device receives a packet and its time to leave is equal to 0, it will discard the packet, right? So this router will discuss the packet. So this guy will know that, oh, there are more hops in my route. So let me increase the value of time to leave to now 2. So he will increase and will send another packet to trace the route. So it will come when it is 2 here. It will leave when it is what?
1.
When it is 1. It will be received here when it is 1. And it will leave when it is what?
0.
When it is 0. Will this guy receive the packet?
No.
So this guy will go ahead and disregard the packet. So this guy will now know that, oh, it means that we have so far identified 2 hops in my network, meaning I still have more hops along the way. Let me now increase my time to leave value to what now?
To 3.
To 3. So it's going to go ahead and increase his time to leave value to 3. Oh God, my pen, to 3. So after increasing the time to leave value, this time round, it will go through. work it out together. So it will come here. It will be which value?
3.
Our time to live will be which value when it's being forwarded?
2.
And here?
Will be 2.
2.
Be 2. And here?
1.
1.
How about here?
0.
1.
Okay.
1.
Okay. And here?
0.
And here?
0. It will not receive.
It will not receive.
Disregarded.
Yes. So now this guy will know that, oh, I have so far identified 3 hops in my route, but I need to now increase my,
By
time.
4.
So it's going to increase the time to live to
4.
4.
So we go again. Here it's going to receive the packet. Router A is going to receive the packet with what time to live?
4.
I will send it with
3.
with 3. Very good. And here?
3.
And here?
2. Backward 2.
2. Sorry. Okay. And here?
2.
And here?
1.
And here?
1.
1.
Here?
1.
0. But since this is not a layer 3 device, it will go ahead and will receive the packet. So this guy will know that if I am using this route, I have how many hops on my network?
4.
4.
I have 4 hops on my network. So it would also do the same here, and it will realize that if I use this other route, I only have 3 hops on my network. So meaning this other route is the optimal route to host B. And that is a function of trace route. So we are saying here that it also has some other parameters, these other parameters which you can choose to configure to be more specific depending on what you want to achieve. But A, which stands for source IP address, we already looked at it. And F also, in case you want to, to play with the default time to live value and you want to increase it and you want it to start, let's say, from 3 or something, you can
have a session with him.
You can always choose to play around with those devices, and of course, maximum time to live value. Time to live value, you can also say that you say, if you have more than 30 hops or 40 hops, I don't want anything to do with that route anymore. Like it should be the max term. And then of course the name and etc and etc. And of course the P is going to P is here. The P is basically the port, the minus P, the port, and specifies the UDP port number. Right? The P specifies the UDP number, and this is the default port number for that UDP. The maximum time to live is usually 30, and the default time to live, the first time to live, 1. Right, so someone is having a microphone that is acting up.
Can those who mute their microphones, they're giving us feedback.
My co-host has disappeared, but I will go ahead and mute. All right, thank you for muting. So we are saying that the trace route command displays each hop that the packet passes through during network transmission. We won't spend a lot of time here because we are typically not network engineers, but basically this is how it looks like. So it will show that I have gone through this hop, I have taken this amount of time, and this is what I've taken, and it will give you a break of the time it took with the default configured values of trace route to this host here, which is B with an IP of 30.0.0.2 with a /24, and then it will tell you the default configured values, and it will go ahead and calculate and looks out the route for you. So the routing protocols. Routing is the most basic element in data communication network. It is a process of selecting paths to a network through which packets are sent from one source to a destination, right? So we are looking at this routing. It is a protocol that is concerned with selecting the path. Like, which path should we take? How are we going to make sure that these guys are not going to keep on looping and looping and looping and looping until like forever? So routes are classified into following categories. We have our network segment routes. The destination is a network segment. The subnet mask of an IPv4 destination address is less than the 32 bits that we all know. And the one of an IPv6, IPv4 version 4, IP version 4, we're saying it is less than 32. And then IP version 6, we are saying that the destination address is less than 128 bytes, yes. So then we also have our host routes, and the destination host is a subnet of an IPv home address, and it's still same concept. And the routes are classified into the following type based on whether the destination is directly connected to the router or is not directly. So we have what we are calling the direct route and the indirect route. So with the indirect route, a router is indirectly connected to the network where the destination is located. With the direct route, a router is directly connected to the network where the router is located. Here, direct, like you hear the word direct, it is directly connected with the network. With indirect, it's not directly connected with the network. Maybe also what we can look at is the unicast routes. We have the unicast route and the multicast. What comes to your head when you hear multicast? To your mind when you hear multicast?
Many.
Yes, here we have the destination address is going to multi addresses, yes. And unicast?
One route.
Yes, one or a unicast address. So basically, that is it. So we're going to look at some of those protocols. But one of them is the OSP. Who knows OSPF in full?
Open shortest path first.
Open shortest path first. No stories. Open short fast. Open short path first. No stories, right? And this protocol helped us to, deal away with loops. It helps us in fast convergency, good scalability, and of course, it also supports authentication. With this protocol, it is a routing protocol based on the link status, and it ensures that the network topology is loop-free. OSPF supports an area vision, and routers in an area use the shortest path first algorithm, and I think that's why they called it the OSPF. And they do so to ensure that there is no loop in that area. They use the open, the shortest path first. And this OSPF also uses an interconnection rules to ensure that there's no routing groups existing between also those areas. And it can also trigger an update or to detect. It also helps to detect if maybe one router has gone off. They will still go ahead and they will go through the election and they will choose who is going to be. We don't want to get into that detail, but basically that is how it works. To also be able to detect if there's any kind of router that has gone off, and it will be able to detect, and it will be able to get the different areas and elect among themselves. So let us look at SNMP. SNMP is used to transmit management information between the network management systems and the managed systems, right? It's a network management protocol, and we said it is widely used in TCP/IP, and it enables the network management station that runs the NMS to manage the network devices. So it supports the following operations, of course, sending configuration information to network devices, and also querying and obtaining network resource information through the protocol, And of course, also proactively reporting alarm messages to the NMS and to the network administrators so that they can quickly respond to the network issues. So this is just basically a simple architecture. It includes the NMS and the agent and MIB. So what do you think NMS stands for? Network engineers?
Network monitoring system.
Network monitoring system, perfect. What do you think MIB stands for?
Management information base.
All right, so an agent is a process performed on the managed devices, and an MIB is a database that contains the variables maintained by the managed devices. So we have basically this is more like an architecture of network of operations and maintenance. Understand the traffic trends. You need to understand the traffic trends of all branches and identify the devices that the branches need expansion. These are some of the things you should concern yourselves with. Analyze the distribution of branch traffic. How is my traffic moving through my branch? And identify the value points of capacity, and rank changes in branch traffic and allocate existing network resources accordingly. Also here, we have your different branches. This is just your headquarter. You're connected to your wide area network access, and you're connecting through your different routing points to your branch 2 and branch 1. So as an IT engineer, a branch has exhausted, you go to your manager and you're telling your manager that the branch has exhausted its bandwidth on XY port, and we need to purchase a new device to expand the network capacity. Usually supervisors, them being supervisors, they'll always try to find means of, cutting costs. So they'll try to talk you into thinking through if you have actually done your job correctly, right? So are you sure we need to expand the capacity? Is a network fully optimized, or is a service application developing rapidly? So as the IT engineer, if you're good at what you do, of course, you say, I have a detailed application development report for each branch, and I have done all my research work and I'm ready, so I know exactly what I'm telling you or what I'm talking to you about. So we look at NAT. So the basic concept, NAT concepts and function, but we're going to look at the basic concept. Remember, this is not a networking course. What comes to your mind when you hear the word NAT? Network engineers, you can bail us out.
Network traffic analyzer.
Network traffic analyzer. So the eSite network traffic analyzer, sometimes people call it the ESNAT, and is a software only solution. No hardware probe is required and no additional investment is needed according to this document. So that such the NetFlow, NetStream, and SFlow protocols are used to collect and analyze common IP packets, provide a customer analysis report, and monitor network-wide traffic in real time. This is a powerful tool for enterprise operations and maintenance management. The functions of this is basically, it provides a convenient way to monitor and analyze our networks, right? What are the functions of eSite NTA? It is to what? Monitor and analyze networks. By using the IP network traffic information provided by network devices that support NetFlow, NetStream, and SFlow, the eSite NTA analyzes network-wide traffic and provides traffic analysis reports and displays traffic analysis results in various charts. This helps users to learn about wide traffic, including the traffic distribution, and detect network traffic. Are we together?
Yes.
Right, so we proceed to the next slide and we see what's there. So proceeding to the next slide, we have the NetStream, which they were talking about before, and we are saying that the NetStream is a Huawei patented technology used to collect and distribute statistics about the network traffic, right? NetStream used to collect and distribute statistics about the network traffic. The NDA sends the obtained statistics to NCS for further processing and then sends the statistics to the NDA for analysis. The results for the analysis provide the basics for network accounting and planning. You have your NDE device which sends the obtained statistics to the NC, and the NC then for further processing sends these statistics to the NDA and the NDA for analysis. But basically this is a Huawei solution, and I will not spend a lot of time on it. So let us look at some of the common transport layer protocols. TCP. We said it's it requires a connection for you to be able to communicate. Before you communicate, you must have a connection, isn't it, right?
Yes, not
Let
like
us look.
UDP.
Yes. So let us look at the three-way handshake for the TCP. To establish a connection with TCP, it uses a three-way handshake process, and this process is used to confirm the state sequence number of the communication parties to the subsequent communication, so that subsequent communication can be performed in an orderly manner. The process is as follows, like the way you see it on the screen. So when the communication starts, our client here, A, it sends out a SYN message. Sends out a SYN message to the server, and the client sets the SYN sequence number to a random value, which is, this is a random value A. So it sets our sequence number and sends our SYN message to our server here. And our server is going to receive this SYN. So after receiving our SYN on the server level, the server will also go ahead and reply with a SYN plus our acknowledgement, and also it will go ahead and set our acknowledgement number, let's say as the received sequence number, plus it will add our sequence number which was received there, and it's going to go ahead and add a +1 on it, and then the sequence number as a random number value B. It's going to come up with this random number value B. So it's going to, our client is going to send a SYN. Our server is going to reply that, oh, I acknowledge, SYN plus the acknowledgement. It's going to get the acknowledgement, add this sequence number +1, and then it's going to go ahead and also come up with its own sequence number. So after receiving at the client's level, after receiving the SYN plus acknowledgement, the client will now acknowledge that, you know what, I think we are now good to go. Thank you for replying. I can now start sending you my details. So it's going to go ahead and get its sequence number +1, and it's going to get the acknowledgement number will be the sequence number of the server. It's going to add 1, and then the server, after it receiving the acknowledgement or the ACK packet, then a connection would have been established according to the TCP connection three-way handshake. All right. So basically, in summary, client sends SYN, server responds with SYN plus acknowledgement, and then the client finally responds with acknowledgement to complete the connection. Let us also look at disconnecting the TCP connection. So when disconnecting the TCP connection, unlike the three-way handshake for establishing the connection, this time around we have a four-way handshake for disconnecting the connection. So to terminate a connection, TCP uses a four-way handshake process, and this process follows. The client will go ahead and send a FIN packet. After sending the FIN, the server will reply with an acknowledgement +1 packet. It responds with the acknowledgement +1 packet, and the server sets the acknowledgement number as received sequence number plus the acknowledgement number. So, and then it enters the closed wait state. So after entering the closed wait state, it will still go ahead and send the, it will still go ahead and send send the, wait for the client to send the, the remaining data, and it will go ahead and send the fin plus acknowledgement. And after that, sending the fin plus acknowledgement, then our client will respond with the, will respond with acknowledgement, and then our TCP connection will be closed immediately. And application layer, we have quite a number of them. We have HTTP. We talked about HTTP or HTTPS. HTTP or HTTP or HTTPS, which refers to Hypertransfer Protocol, which protocol is used to browse our web pages. We talked about our FTP, IFTP protocol, which is a file transfer protocol, and this protocol is used to upload and download file resources. And we talked about our DNS, and our colleagues told us that it refers to the domain name resolution protocol, which is used to resolve domain names to IP addresses, right? These are some of the common protocols. So if you are connected on your computer, on your switch, let's say a router, which is also connected to the domain name server, it will translate the IP addresses to the name which you can best understand. And of course, you can also be able to connect and use the FTP protocol to access files from your server, or use the HTTP or HTTPS to access, files through the browser. And who knows some of the mailing protocols that we can use?
SMTP.
Is come again?
SMTP.
What else?
For sending mail, pop-ups leave for people.
IMAP.
All right.
IMAP.
IMAP, and so on and so forth. All right. So this is how the domain name resolution works. It is performed by a dedicated domain name system. The domain name system involves the following types of servers. There is a root server, top level domain server, and of course the incursive server and cache server. I'll just go through these briefly. So the cache server, I don't know about this. I have to ask the experts. If a client sends a request, I would like to visit www.huawei.com. Then this guy will be like, you know what? I don't know about this. I need to first consult the experts. This guy will go ahead and consult with the expert and ask the top level domain name server that what is the IP address of the corresponding www.huawei.com, because computers don't understand the words. This guy will say, don't worry, the IP. Someone please mute your microphone. Would someone please mute your microphone? Could someone please mute your microphone?
Samuel, why don't you mute them?
Okay. All right. So, and then this guy will respond and say, the IP address to Huawei.com is this, to the server of Huawei.com is that. Kindly, you can forward that to that guy. And then also maybe what is the corresponding IP address if it's consulting the root I, and then they say the IP address to the server, to the DNS server is this. If it doesn't have the IP address to that of Huawei, and then of course, Huawei will be able, this guy, maybe just to explain it in order, this guy will first talk to the root server asking, boss, help me with the domain to the DNS server of this of Huawei.com. What is the corresponding IP of Huawei.com? This guy will say, you know what? I cannot help you, but you know what? You go and ask this DNS server to help you. This is the IP address. And this catch server will help us to go ahead and ask our DNS server and asks it, you know what? You kindly help me with the IP address for this. And then it will go ahead and tell it that, you know what, the address of Huawei DNS server is that. And then it will go and it looks at the recursive server where this domain resolution is stored and ask what is the corresponding corresponding IP address to this. Kindly help. And this guy will say like the corresponding IP address of Huawei is z.z.z. And then after getting it, he'll be like, you know what, computer, I know you don't understand Huawei, the word Huawei, but the IP address for Huawei.com is this, and it will be able to, you know, establish the connection. It will be able to send the packet to the server and also be able to receive the packets to the server. But the next time this guy tries to visit, the catch server already remembers. Yeah, I remember it, so it will not go through the process of finding out the IP address of that domain. So it will just go ahead and say, remember it, please just use this is the IP address. So you can go ahead and send your packets to the server. How FTP works? FTP provides an effective way to upload and download files between a server and a client. Yeah. So when FTP is used to transfer files, two TCP connections are used. The first is the control connection between the FTP client and the server, and this is enabled on port 21. The FTP server and the client wait for the FTP client to send a connection request. The FTP client enables a random port and then sends a connection request to the FTP server. The control connection is used to transfer control commands between the server and the client. So the second one is the connection between the FTP client and the server uses the FTP, TCP port 20, right? And if it uses port 20, then to establish a data connection, then with the client, generally the server actively establishes or interrupts the data connection. Because FTP is a multi-channel protocol, a random port is used to establish data channel. If a firewall exists, the channel may fail to be set up, right? So this is just a system showing you the user trying to access the user interface. And we have here where there's a process control and there's a data transmission process. And we have our servers and of course they're accessing different file systems. So FTP transmission mode, we have talked about these modes. We said that if FTP supports, it supports two modes, active mode and passive mode. In the active mode, which is used by the default, the client has to set up a connection and the server sets up the data connection. In the passive mode, the client sets up both the connections. Users can switch the mode through different commands. Yeah. So FTP connection set up in active mode. So temporary port connection mode, then data, either you can connect through either port 21 or port 20. All right, so FTP transmission mode 2, FTP, this is the passive mode. They're just showing you here. We say that in the passive mode, the procedure to set up the connection is you just go to the server and enable port 21 to listen for the data and wait for the setup control connection with the client. So the client sets up initiates a control connection setup request. The server will of course respond. The client will then send the command to the control connection to notify the server that the client is in passive mode, and then the server responds and informs the client to temporary of the temporary port to be used for the data connection. The data connection is set up between the client and the temporary port of the server. HTTP and HTTP basic concepts of the web. I don't find it important going through this. Should I just go through this? But as you can see, it's just basically this, right? You know what a uniform, uniform resource locator, URL, you know HTML, you know HTTP, right? And you know what www is, and yeah, the rest and so on and so forth.
Yeah, okay.
All right. So HTTP is a stateless protocol that uses a request to respond method to the communication. It sends hi, and then it will go ahead and say, I need the file X, and then it will go ahead. It says hi, and the browser, of course, the server responds, what can I do for you? I need the file to get this file. And then he asks, do you have the key to get the file? This guy says, I have the key at this key. And then this guy says, okay, here's a file, go and play with it. So HTTP has two types of packets, the request packet and the response packet. The request packet is sent to the client, it's sent from the client to the server, and the response packet is returned from the server to the client. We talked about this. You gave me these examples before, how mail is sent and received. So SMTP defines how PC sends mail to SMTP server and how email is transferred between the SMTP servers. Whereas the Post Office Protocol 3 and Internet Mail Access Protocol specify how PCs manage and download mail on the mail server through client software. So the SMTP and the POP3 or IMAP are developed on mail server by the administrator, and a mail client software such as Microsoft Outlook is installed on the user's PC. I also move to the quiz and ask you, let me pop up the poll. Let me pop up the poll, let me pop up the poll, let me pop up the poll. Are you seeing it now?
Yes.
Kindly do. Question 1 is saying, which of the following is not in the TCP IP model? Kindly go ahead and find that poll and answer. And then question 2 is saying, which of the following packets is the first packet of the TCP three-way handshake? You also go ahead and answer. Right, you have about 5 minutes, then we talk about them. Are we done? Are we done? I'm only seeing 45, 46 responses. You have less than 3 minutes
Yeah, we are done.
already.
Yeah.
Okay, I'm waiting for our colleagues to also finish up. All right. I will end the poll here and see how we have answered. I've shared the results. Most people said that it is a session layer. And of course, you're 100% correct, right? You're 100% correct. This layer is not part of the TCP/IP model, but it is part of the OSI model. It is the what layer in the OSI model?
Application.
No, it's at what layer in the OSI model?
Layer 5.
Layer 5, yes.
Layer what?
5.
Layer 5, eh? All right. So, and then let's also look at question 2, which says, which of the following is the first packet of the TCP three-way handshake? Which is the first packet of the three-way handshake?
SYN.
It is, of course, SYN. You just saw. It first sends a SYN, then the guy sends with the SYN plus acknowledgement, right? Plus acknowledgement. Then finally, he sends the what? Then he sends the arc, right?
Yeah.
Sends the SYN. Okay.
The arc.
So it is SYN, right? I've seen some people selected other things, but the first packet is the SYN. What is the second packet?
SYN plus acknowledge plus arc.
Yeah, first packet is SYN. The second packet is SYN plus arc. All right. Okay. So that takes us to the end of this presentation, and brings us to the beginning of this presentation. I want to also peruse through this. Most of the things we've been talking about already, and it's common network devices, right? We've been looking at some of those concepts. Now we're going to look at some of those devices, right?
Okay.
Are we tired?
We can continue.
Okay. So we all know that network devices are the best components of a network, isn't it? So when planning and constructing a network, you need to deploy and configure the network devices to meet the network connection or to meet the network security requirements. So that being said, upon completion of this course, you'll be able to describe some of the common Huawei devices, describe the functions of network devices, and log in into devices and perform basic configurations. But we're not going to do this in this chapter. I will cover it in our detailed practical session. So basic network devices. We have talked about, let me stop sharing the results and close the poll out of here. But we have been talking about them and mentioning them and saying this, that. But you know, in any network arrangement, you will at times find routers connected in your system, isn't it? Routers or layer 3 devices. And we said, what are routers?
Morning.
What are routers? Anyone?
Devices work at in layer 3. Use the best
Device
path.
for communication across a network segment.
Okay, routing across
And
networks. Right,
yes.
okay. And we also looked at different switches. We looked at switches, right? And we said, what do switches do?
Word packets.
They connect different devices, the network.
At which layer?
Creating frames responsible for hop-to-hop connectivity.
for connectivity, and they're at layer 2. All right, we didn't talk of, okay, we didn't talk of the anti-denial of distributed denial of service, but it is a system which is deployed at some networks, specifically at the egress level, to help to help upstream, to help reduce on some of the load of the firewall, right? So that the firewall does not have to process so many of those things. And how about a firewall? What is a firewall in your understanding?
It's a preventive measure put in a network to protect the device from given threats.
Okay, preventive measure. And we can see we have a virtual, we can have our virtual firewalls, and we can also have our different firewalls.
Firewall just monitors any coming and outgoing traffic.
Okay, yes. So this can be deployed at networks to provide preliminary protection or to protect data centers from attacks. Also, virtual networks like virtual firewalls like this one, they can also be used in virtual machines, and they have also similar functions of the hardware firewalls, right? The NIP, they are the network intrusion prevention. Some devices that can be used, and they are used in a Huawei developed intrusion system, and they prevent devices that can be deployed in data center to provide protection against the devices that can be deployed in a data center to provide protection against intrusion, and so on and so forth. And of course, computers, VoIP, voice over IP, Apple computers, what, mobile phones, laptops, etc., etc., and so on. So let us look at a switch. We said a switch works at a data link layer, which is layer 2, and forwards data frames, right? If we have our host A, host B, and host C, and they want to communicate, we need to have, of course, we connect different users on these networks, but if these guys need to communicate, then this guy has to send packets and forward packets to different switches. So our switch has 3 different modes. It has the flooding mode. It has the flooding mode here. It has the forwarding mode, and it has the discarding mode. What you should take note of the flooding mode is that when our switch receives a packet, it can, in a flooding mode, it can flood the packet to all other interfaces on it, except the interface which received the packet. In the forwarding mode, still, same scenario, the switch can forward the frames received on an interface through other interfaces, but it does not forward through the interface which has received it. And in discarding mode, the switch discards the frame received on an interface. So if you configure an interface and you put it in a discarding mode, it will definitely, of course, will not allow to receive packets, and it will discard them. So the basic working of principles of switches are as follows. So upon receipt of a unicast frame, the switch searches the MAC address table for the destination MAC of the frame. So if the MAC address cannot be found, then the switch will, of course, flood the frame. But if the MAC address is found, then the switch will forward the frame if the MAC address is not on the interface on which the frame was received. Otherwise, the switch will disregard the frame. Those are some of the states of the switch. So the initial state is that the MAC address table is empty on our switch. It has not learned of any MAC addresses in our network. So as this guy, host A, tries to send a packet and communicate to try to communicate to other packets. Is it, do I have like animation? I don't think I have animation. Let me first try and see. Okay, there's no animation. So what it does after this guy sending his source MAC address with the destination MAC address, he sends an ARP, yeah, right, trying to find out who is trying to reach. If he wants to reach, like, let's say another host, what will happen? This guy will get his MAC address and he will store his MAC address in his MAC address table, and he will also store the interface on which this computer is connected. Say interface gigabit 001 is where this guy is connected. So he will store him. So as this guy, as the packet, when the destination MAC address of the data frame is not in the MAC address table, or it is in a broadcast address, the switch floods the frame. So if it comes in this an ARP, it's in a broadcast mode, or if the MAC address is not on his table, he will also flood the packet. He will send it to other hosts connected to him. He will send it to other interfaces. So host B will receive and host C will receive. So this guy will receive, and then after receiving, this guy of course will send back a response. Remember, this guy will disregard the pack because he will look at the IP address and it's not his IP address like we said in the previous slide, so he will disregard the packet. And after disregarding the packet, this guy will send back the unicast response to this guy, but in the process of sending back, this switch will learn of his MAC address, and he will also go ahead and update his MAC address table and put him there. He's connected on gigabit Ethernet port interface of G003, and he will store in his MAC address table. And next time, if these guys wanted to communicate and send, he will not now need to forward. He will know, oh, I know the guy who you're trying to communicate to, he's on this interface, and he will just go ahead. He will not flood the entire network, but he will just go ahead and send the packet to this guy because he knows this guy is connected to this interface. Function, forward data packets between different networks. You know, there is some bit of routing, so the application layer will play its route, and then you go to router A. The router A will go through the process, the route until when you get to the host, which has now these layers. Data decapsulation works. So a router selection, a router selects the optimal path. I hope we talked about what a router is. A router, it performs, it forwards packets between different networks. It forwards packets between different networks. And of course, it also selects optimal path for data packets and forwards the packets. It will select the best path and it will forward the packets. Of course, the firewall, you already told me, it was mainly introduced in the first stages against attacks and intrusions from other network areas, right? And yeah, so but mainly in communications, the firewall is used to protect one network against other network attacks and intrusions from other network areas. So because of this isolation and defense capabilities, it can be flexible, applied to network borders and subnet isolation, for example, enterprise egress level, or also an internal subnet isolation and data center border. All right. So comparing firewalls with switches and routers, the primary function of routers and switching is forwarding, whereas that of a firewall is controlling, controlling traffic to make sure this traffic, is it performed to go through this? No, this one block, this one is allowed, this one is not allowed. Whereas the routers and switches, for them, their primary purpose is to do forwarding. So this is the development of the history of firewalls. I'll ask you to go ahead and read through them. There's nothing much really to talk about them, but you can read it through them in your free time. I'll share the PowerPoint. And also the firewall has security zones, but the functions of security zones, the policies are implemented based on the zones that we created. Data flows in the same security zone and brings no security risks, and therefore require no security policies. So the firewall performs security checks and implements security policies only when the data flows between different security zones. So all devices on the network
Bluetooth mode.
Okay, someone's Bluetooth failed. Zone may contain the network connected to multiple interfaces. So usually the default security zones like the trust zone, local zone, the DMZ, and of course untrusted zone. So the relationship between security zones and interfaces is that does a firewall have two security zones with the same security level? Does a firewall allow the same physical interface to belong to different security zones? Can different interfaces on a firewall belong to the same security zones? These are some of the questions that they're asking us from here. But all devices on the network connect to the same interface and must reside in the same security zone. And each security zone may contain networks connected to multiple interfaces. So the interfaces can be physical or logical. Users on different network segments connected to the same physical interface can be added to different security zones by using logical interfaces such as sub-interfaces of the VLAN if interfaces. So that takes us to the end of that. The device initial logins, we shall look at them in the subsequent coming classes. So having said that, I want to thank you for being part of this class and to thank you for giving me good audience and for everything.
Wow, that was great.
All right. So we shall start from there tomorrow. Someone is having feedback, but if you could kindly
Mute. Before you go, maybe I was inquiring. Like,
yes,
I'm a guy from evening, but there is I might not be there in the evening, but I've fully attended this session. Is it
That's
possible?
okay.
Is it okay?
That's okay. Your attention has your attendance has been recorded.
Okay, sir. Thank you.
All right. Thank you, guys. Allow me to run out of this meeting. It has been great. We shall start from there tomorrow, same time.
Okay.
All right. Have a good day.
Right. Thank you.
Good day too.
All right.
Bye.
Bye, Brenda.
Bye-bye.
192.0.1.